Okay. Good morning, everyone. So first of all, let me ask you, how was the exam? It was hard. You sure? Actually, I forgot what I asked, but I think the first question was what? Sequences, about sequences. Whether the sequence is divergent or convergent. So just the limit questions. Just the limit questions. You just take the limit of the sequence. If you have a limit, that means it is convergent. So why it is, I don't understand why you are saying it is difficult. Limit means the first semester course, Calculus 101 subject. And then you have questions about series. We ask you some series to check whether it is convergent or divergent. Yes. Actually, it's still the exam paper is not finished. My colleague is still checking his questions. Then he will give me the papers and I will check my questions. And I think at the weekend, we are going to finish it weekend, finalize the weekend, and we announce the results on weekend. Okay? This is the first thing for today. Sorry? Yes. I announce everything on Uzabim. And the second thing, on weekend, you will have a quiz, online quiz, okay? Online quiz this weekend, online quiz about actually midterm subjects. So you already studied because last week it was midterm. So you're already ready. You are ready actually. So always I am telling you, please check your online book, whether it's work or not. And if it is not work, try to fix it before the quiz. Okay? Now, today, new chapter. We are going to start new chapter. Partial derivatives. Partial derivatives. But before seeing the partial derivative, let us talk about the functions. Functions of several variables. Functions of several variables. Till today, the function we use was a single variable function. We have only one independent variable, x, okay? F depend on x. And we take a limit of the function, we find the domain of the functions, then we find the derivative of the functions, then we integrate single variable functions. And now we start again from the beginning, again, okay? But this time our functions has many independent variables. So let's first give a definition. A function f on n variables is a rule that assigns a unique number f of x1, x2, xn to each point x1, x2, xn in some subset D. D here is domain, in some domain of Rn, n dimension, okay? If your dimension is 3 dimension, R3, we have 3 dimension. That means you have X, Y, Z only. D is called the domain of the function f, and the set of real numbers f obtained from the points in the domain is called the range of f. So, graphical representation. Actually, why we need multivariable functions? In a reality, our functions, whatever the function is, maybe your profit functions, maybe it is about the heat. It represents the heat, for example. Maybe it represents another things. You depends on some variables. Okay, for example, in economy, or if you produce, for example, what produce cheese, for example, you have white cheese, you have Hellenic, you have yellow cheese, you have different types of cheese you have. Okay, so you want to get more money, you want to make your profit maximum. So you just observe how many kilogram you produce white cheese and how many kilogram you should produce from the Hellenic to get the maximum profit. Okay, so to see this, first you have a functions, and these functions should be a multivariable functions. If we show it in graphical representation of the functions, in single variable functions, remember, we have x and y axis. We have x and y axis. And we have just a curve. Okay, we have a curve. So the function represents a curve here. F of x is a curve here, whatever f is. But three variable functions, our functions this time, the picture here is not a curve, it is a surface. We call it, it is a surface. Okay, surface. And in the single variable functions, the domain is what? Domain is all possible x values that the function can take. All possible x values. So if we have f of x, so we want that which x we can use in this for this function. So in multivariable functions, now especially if we have three variable functions, x, y, z, okay? Now we want to know which x and which y can we use here. So now the domain is here. Domain is here. Okay? So every point on the surface, if you project this point to xy plane, so it should be somewhere here. So we call this domain of f. Okay? This is a graphical representation of three variable functions. So in three variable functions, we don't have curve, we have surface. Okay? This is surface. Remember, think about the airplane. So its shadow reflects to the ground. Okay? So in the ground, it is 2 dimension, but in up, it is a 3 dimension. So this is something like that. Okay? Now, if you look at from the top, you'll see its shadow on the Earth in two-dimension space. Actually, drawing a three-dimensions picture is difficult, right? It's normally difficult. It's not easy to show it, to draw it actually, but you should know at least some surface. You should know it. Okay, for example, cylinder, sphere. You should know it. Conic picture. You should know it, right? So I will show you this now. So the graph of a function f of one variable is the set of points in the xy plane having coordinates x and f of x and y, as I explain you, where x in the domain of f. Similarly, the graph of f of two variables, z, is the set of points in 3 space having coordinates x, y, z, where z means f of xy, where xy belongs to the domain of f. The graph is a surface in R3. Okay, so we said R3, not R cube. We should say R3, all right? R cube is different. R3 is, that means 3 dimension. If you look at this example, the z here, f of xy, is equal to 3 times, in the parentheses, 1 minus x over 2 minus y over 4. This is our z, okay? And the domain is x between 0 and 2, y is between 0 and 4 minus 2x. So if you put x0 here and y0, if you start this, x and y0, then you get a z direction. I mean z here, 3. Okay, you get a z, which is 3. Then if you say y is 0, z is 0, then you get x. And similarly, if you say x0, z0, you get y from here, here. And then if you connect these two, these points, you will get a triangular surfaces with vertices 2, 0, 0, 0, 4, 0, and 0, 0, 3. So this is triangular surfaces, okay? This is triangular surfaces with domain of this one. Another example, this time consider z is equal to, in the square root, 9 minus x squared minus y squared. All right? So actually, if you square root, in the square root, 9 minus x squared minus y squared. If you square both sides, what you get? You get z squared equal to 9 minus x squared minus y squared, right? And I can write this as x squared plus y squared plus z squared equal to 9. So this is the equation of the sphere. This is the sphere, equation of the sphere, center 0, 0, and radius 3. Like if z is 0, we have x squared plus y squared. That means that it is a circle, center 0. Okay, so when you add the third dimension, z squared, you get a sphere. All right, we get a sphere. A sphere, but as you see, we have here only plus square root. Actually, we should have plus and minus, but in the question, it is plus. That means it's the upper sphere. It represents the upper sphere, okay, upper part. So what is the domain here? Domain is here, then all possible x and y values. Okay. So what we know that in the square root, we should not have a negative number there in the square root. So that means this term here should be positive or equal to 0. So it is, as you see, that means x squared minus x squared y squared should be less than or equal to 9. This is domain. So the domain is the disk. X squared plus y squared less than or equal to 9 in the xy plane. Okay. And the picture is a sphere of radius 3 centered at the origin. However, the graph of F is only the upper hemisphere, where Z is positive there, as I explained you. So if you see the picture is something like that. So a sphere, when you have a sphere, you just draw it roughly in this, like this. Just draw it like this. That's it. This is sphere. Okay? This is sphere. And if you look at the sphere from the top, what you see on the circle, you see the circle, something like a circle. Suppose you have a glass. You just look at the glass from the top, you will have a circle only. Okay? So this picture here, the red here, it is a circle. When you look at it from the top, here, you see this circle here. That means we have a circle. Circle, radius 3, center 0. Okay, so this is circle. This is the domain. XY plane. This is the domain. Okay, after seeing what is multivariable function, how it's graph, then how we define a function, how we find the value of a function. It's exactly like as single variable. You just substitute x and y, you get z. That's it. Nothing else. Okay. So we have this. So in part A, it says that sketch the domain of f. Sketch the domain of f. So what we know, domain of f in 3 variable function is the set of all x and not all, all possible x and y values. So that means this term here can never be 0. Okay, can never be 0 because something over 0 meaningless. So it can never be a 0. So that means that y minus x squared should be positive, never be 0. That means y greater than x squared or x squared less than y. So this is the domain. This is the domain. So the graph of domain is the set of all points that lie above the parabola. So we have parabola. So above the parabola here. This is the graph of a domain, not graph of a z function. This is graph of a domain. Okay, graph of a domain. So to find the values, when x is 2, y is 5, you just substitute f and you get 5 over 2, for example. Okay, so this is the one way of represents the curve actually. What I mean is this: you write an 2-dimension here, x and y, and for the third dimension, you draw another axis here. This is w, let's say. So this is the third dimension here. You can express it in this way as well. Okay. So you just substitute some values, you get f values. You substitute this, you get f values. This is how you find the value of a function. Any question here you want to ask me, guys? So up to here, what we've seen, we learn what is a multivariable function. We learned some types of graph of a multivariable functions, and what is domain of multivariable functions, and how we find the value of functions. Now look at here, look at this picture now. Suppose we have again a surface like this. We have a surface, all right? And then you cut this surface with a plane, by a plane, okay? You have a surface and you cut this surface with a plane. When you cut with a plane, you cut it the point K, for example, okay? You have here a trace. You will have here a trace, all right? And all points on the trace, when you project it to XY plane here, you get a curve. We call it a level curve. We call this curve a level curve, okay? Level curve. So consider the trace of the graph of f on the plane z equal to k. If we project this trace onto the xy plane, we obtain a curve C. Okay, this is actually C, but script C, like this. It's a curve with equation f equal to k. Note that, note that if a point xy 0, I mean here, if a point on this curve, on this level curve, moves along the curve, moves here, for example, the corresponding function values f always equal to k. What it means, if you are here, you are here. That means on this k. This is z equal to k plane. If you are here on this on the level curve, then the value is here. Always the value is k. F equal to k. F equal to k. So look at this example. Let a function be 9 minus x squared minus y squared with domain D. D is equal to x and y, such that x squared plus y squared is equal to 9. So this is domain. All such a x and y, where when you add them up, when you square them and add them up, x squared plus y squared, it is less than or equal to 9. First, sketch the graph of f. We want to sketch the graph of f. Okay, again, think about the single variable. If you have y equal to x squared, what is it? Parabola, huh? It is parabola. Parabola, concave up shape. If y equal to minus x squared, it is parabola in concave down shape. So this is the same, exactly the same. Here, z equal to x squared, y squared. So that means it is some kind of parabola. It is a downward. Okay. When x0 and y0, you find z values. When x0 here, y0, you get z equal to 9. So start from 9. Start from 9. And you just draw a parabola like this. Okay. So sketch the graph of f. So we sketch the graph of f. In the 3 dimension, we change the name of parabola. We call it paraboloid. Okay. we not say parabola, we call it paraboloid, right? So this shape is called paraboloid, right? Paraboloid. Now then it says that the part B, show the traces on the planes Z0, Z2, Z4, and etc. So we want to show the traces. Traces what? When you cut the surface, you get a trace. Okay, we get something on the curve. So when Z0, this is Z. When Z0, when this is 0, this means what? X squared, Y squared equal to 9. It is what? It is a circle, center 0, radius 3. So here, a circle, center 0, radius 3. When Z is 2, just put it here 2, okay? And then make necessary calculations here. So you have another circle like this. So you have another circle like this. You cut it, okay? So we have many circles. You get many circles. So this is Z equal to K, the trace, Z equal to K. That means K equal to 9 minus X squared minus Y squared. So depending on K, K0, K2, K3, K4, whatever it is, you get this radius. The last part is sketch some level curves. Level curves. So level curves are the curves which the trace projection on the XY plane. Okay, so you think about, you have a circle, 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 circle. When you look at from the top, you'll see in the ground many circles inside each other, like this. Circle, 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 like this, okay? Because you don't have third dimension. So you will see like this. And actually, especially you use it many in the application, especially mapping, for example. When you look at the map, you can see the mountains. They show it mountains, browns, dark browns, then light browns, more light, more dark, and etc. So that means that the small one means the highest point, or in the ocean. When you look at the map, you will see the ocean, okay? But some different color of blues, for example, okay? This shows that. Or in the radar, for example, when you have radar, you have circle, 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 and you see the where the object is using radars. So you can have a question in exam like this, similar, okay? I give you a function. I said, draw the graph of a function, find the traces, and find or draw the level curves. Exactly like that, okay? Okay, this is the first section of this chapter. In the first section, we explain, we see what is the function of several variables, the domain of the function of several variables, the graph, the curve of the several variables, and level curves and traces. Okay, like calculus 101. First, we see they are actually in this university. We start calculus 1. We start from the chapter 1 limit. But normally, some university or sometimes we start from chapter 0. Chapter 0 is about functions. What is a function? What does it mean? Domain, how we find the inverse of the function, symmetry of the function, etc., etc. But we assume that you all know about the function, and we start from the limit. in Calculus 101. Okay. Here we start from the function. I explain you what is a function of several variables. And now we came to the limit. So the limit idea is exactly the same as the limit Calculus 101. Okay? Calculus 101. But there is a difference, of course. So for clarity, we present the definition for functions of two variables only. But if you have three variables, if you have four variables or more, all definitions, all rules are the same. Okay? But to show it in example, to understand more clearly, our example will be two variables function. We say that f of two variables approaches to the limit L as the point xy approaches to the point AB. And we write limit as x and y goes to A and B of f of xy is equal to L. How is in a single variable? Limit as x goes to some number, let's say A, f of x equal to L. Same. But since we have two variables, we say x and y goes to A and B, for example. Okay. So all the properties about the limits in single variable are correct in two variables as well. Okay. That means if you have a limit of f equal to L, and if you have a limit of g, another function g, equal to m, then the limit of the sum equal to sum of two limits. Exactly the same as single variable. Limit of the product equal to product of two limits, and etc. Okay? So all these properties is exactly the same as properties on single variable. And if you remember in Calculus 101, what I always telling you, please first substitute the given x values and see whether we have a limit or not. Before doing something, before trying to simplify or before trying to do something, just substitute and see what happened. Okay? So here again, if you have a polynomial like this, x goes to 2, y goes to 3, I just substitute x here, y here, and you get -5. That's it. Limit is -5. No difficulties here. It's just straight forward, okay? Just straight, put the x and y values, substitute here, and get the answer. That's it. But sometimes, like limits, single variable, we have 0/0 case. We have 0/0 case, or limit does not exist, for example. So you should do something. So here, in this section, we will see how we will check whether the limit exists or not, or how we check whether the limit does not exist. Okay. Look at this example. Limit as this function as x and y goes 0, 0, show that limit does not exist. So the common mistakes you do in exam, here I am saying that show that limit does not exist, but in somehow, I don't know why, you find me a limit. I'm saying that does not exist. Show it does not exist. Why you find a limit? How you find the limit? Okay. So to do this, there are of course many ways. So it's not possible to know each way, but at least here in this lecture, I will show you some methods. So in exam, you use these methods, okay? you start like this. If you are given this limit, one way of seeing this about x-axis. That means that x is x and x goes to 0. Okay, x goes to 0. About x-axis, sorry, about x-axis, that means y is 0 here. Y is 0, x is any x. So you just put y0 here, and we have x is x, so x squared over x squared, which is 1. So limit is 1. Okay. Then this time about y-axis. So about you are going to about y-axis to the origin. You are going to origin from like this. So that means here x is 0 here. So if you put x0 here, then you will get -1. So -1. So you see, when you go to the origin 0, 0 from the x-axis, you get 1, limit 1. When you go to the 0, 0 using y-axis, you get -1. Two different limit. So two different limit means limit does not exist. Okay? Limit does not exist. But sometimes you use this idea and you get the same limit. Then you should find a way to get a different limit till you get a different limit. Because in two dimension, yes, in two dimension, you either goes x goes from the right or from the left. That's it. Right limit, left limit. And they should be equal in order to say the limit exists. If they are different, you say that limit does not exist. But in three dimension or more, you have a point here. So you go this point, maybe using a parabola like this, maybe using such a curve like this, maybe using a line from here like this. So you have many way to reach this point, many. Okay. Yes, I explained it, what I said here. As we can see above example, two different paths produce two different limiting values, so the limit does not exist. And I explain why we have this. There are infinite number of different curves or paths, infinite number of curves or different paths. So you can use it y equal to x line. Your friend can use it y equal to x squared. The other friend can use in some other curve. Okay. So there are infinite number of different curves or paths along which xy can approach A and B. So if two different paths to a point AB produce two different limiting values for f, then we say that limit does not exist. Here, in this example, we can use it polar form. We can use polar coordinate to check the limit, especially if you have x squared plus y squared, x squared plus y squared, always prefer to use polar form. Okay. Look here. If x is r cos theta, we know this. And we know that y is r sine theta. We have seen it in polar coordinate chapter. So x squared y squared is what? X squared plus y squared is what? R squared cos squared plus R squared sine squared. So R squared parentheses, you have what? Sine squared plus cos squared, which is 1. So it is equal to R squared. So here we have R squared. Yes? And then here x squared, That means r square cos square, r square, put it here, cos square, and here minus y square, that means r square sine square, okay? So r square cancel here, each other, and both of them, x, y goes 0, when x and y is 0 here, what do you think? X is 0, y is 0. So if x is r cos theta, when it is 0? Sorry? X, not x. We are here r cos theta. So when r is 0. Okay, maybe your friend trying to say pi over 2, because cosine pi over 2 is 0. Okay, cosine pi over 2 is 0. That means x is 0. But what about y? Sine pi over 2 is 1. So it's not 0. So both of them goes to 0 if and only if r goes to 0. So that's why in the here we say limit r approaches to 0, this limit. And since r square cancel here, cancel each other, and we don't have any other r here, so whatever theta is, when theta changes, answer limiting value changes. When theta change, limit change. If theta is 0, for example, sine 0 is 0, cosine 0 is 1, limit is 1. If theta is pi over 2, for example, cosine theta is 0, sine square theta is 1, so we have minus 1 here. The answer is minus 1. If theta is pi over 4, limit is something different. So you see, theta changes, limiting value changes, so we find different limiting values. That means limit does not exist. Look at another example now. Let us. Now this is same, sorry. Yes, here again, x squared, y squared, blah, blah. Now show that this limit does not exist. Okay, here in the example, again, x, y goes to 0, 0. But it doesn't mean that all the times x and y goes to 0, 0, okay? Sometimes x goes to 1, y goes to some other y values, okay? Just by chance, these two examples, in these two examples, x and y approaches the same value, 0, origin, I mean. Okay, this is just chance. Don't think that always 0, 0. Now, if you think that, let's go along the path x-axis, okay, whatever the graph is, if we go 0, 0 x-axis here, that means y0. Put here y0, this is 0. Put here y0, we have x4. So x is anything, okay? X is anything. Then 0 over something is 0. Okay, the answer is 0. If you go along the x-axis. Okay, what about if you approach the point origin from the up, y-axis? That means x0 there. You put x0 here and x0 here. And again, this time, x0 here, yes, and x0, so y squared. So 0 times 0 over something, again 0. You see, either along the path x-axis or along the path y-axis. You all get 0. But the question is, show that limit does not exist. So I should find one way that limit is different than 0. So what? I said, okay, let's say along the line y equal to x. Okay, but to make it general, I said mx. I mean, this is y equal to x, this is y equal to 2x, this is y equal to 3x, this is y equal to 1 over something x, this is y equal to minus 1 over 2x, and etc. So you have many lines. You can approach to the origin many ways, from the many ways. Huh? Okay, so that means substitute y equal to mx. If you substitute y mx here, what happened? we have x squared times mx divided by x squared times x squared plus m squared. So x squared cancel here. So we have mx over this one. But when x goes to 0, this is 0 over, again, some m. M is whatever it is. M is 4, m is 5, m is negative something. So again, this is 0. So I used third one, but again, I find the same limiting values. So I should continue to find another path. So I said, okay, let's go to 0, 0 along the parabola. So like this, for example, along the parabola. Okay. So whenever you see y, you substitute x squared. So our function becomes, this is, as you know, x squared y. It was like that, huh? X squared y, yes. And where is it? Sorry. X squared y and x power 4, and this is y squared, I think. Yes. And then when you put x squared here, it becomes x power 4. When you put x squared here, it becomes x power 4. So everything becomes what? X power 4 over 2x power 4. That means 1 over 2. So we find that limit is 1 over 2. And if you approach to the origin from this way, you get limit 1 over 2, which is different than 0. So as a result, so not every path leads the same limiting values, and hence limit does not exist. So generally the procedure, the idea is this. You should find any path, okay? There are infinitely many paths. So just find some of them. Maybe you ask me how we know which path I use, because we have many. Doesn't matter. Just actually, I show you some of them here. I show you along the path x squared, along the path y-axis, along the path x-axis. So in exam, use this, or use polar form. Okay, the next example. Again, we have x squared, y squared. So I said, okay, let's use polar form. Substitute x r cos theta, y r sin theta, and substitute there. Write everything in r and theta form. And when you write in r and theta form, and r goes to 0, of course, okay, then what? This cancels. So we have r cos theta sin theta. As r goes 0, it is 0 for all theta. Okay, so the limit is 0 here. Limit is 0. Yeah, in this example, we are not going to show that limit does not exist. We show that limit is 0. Where you go, what you choose, doesn't matter. Limit is 0. So another example. All the limits, all the limit question, you can solve it in this way. Okay. So in this example, we have 3 variables, x, y, z. If you have 3 variables, you can say along the path x, along the path y-axis, along the path z-axis, for example, one by one, you check it. And if you want to show that limit does not exist, you should find one different limit. Okay? So this is about limits. The idea, the concept. You understood, or you have some questions on your mind? Of course, it's not possible to understand everything in the classroom. You should go home, study my lecture notes, open your books, study from there, ask your friends, come and ask me, get the answer, go home, study again, and then you will understand everything. Okay? But the concept is what? Show that limit does not exist. Then you start along the y-axis. You just put the y0 in the function and get what and see what the limit is. Along the path x-axis, along the path y equal to x square, maybe along the path square root, along the path y equal to x line, maybe. So you just use this idea and get the limit. Okay? And then remember calculus 101, after limit, actually, we have what? Continuity. Here in this section, we have continuity part as well, but I skip that part. Okay, you are not responsible. You are not responsible in exam about the continuity of multivariable functions. Okay, you are not responsible, but actually we have it. Then after continuity, remember calculus 101, after limit continuity, we see what? Derivative. So here again, here as well. After limit continuity, we came to the derivatives now. But we call it partial derivatives because we have multivariable function. You differentiate the function with respect to x or with respect to y or with respect to z. With respect to x and y and z stays constant. With respect, if you differentiate with respect to y, that means x and z is constant. If you differentiate with respect to z, that means x and y are the constant. Okay? And the notation here is not d. It is not d. Okay? Not d. We have del z del x. We call it del z over del x, not d. Okay? If you say d, that means single variable. But if you have multivariable, you should put it notation del over del x. Please, all right? And also, the common mistakes you do in exam as well, when you differentiate, you write it in this way. This is what? Function f of x. Function at the value of x. But some of you friends write this as a derivative with respect to x. No, it's not derivative. It is a function. You should know the difference at this, please. Okay, it's very simple things. Okay, so here again, del f del x, or sometimes we say f sub x. That means you differentiate a function f with respect to x. Different notation. Okay, this is del f del x. So here, this is the, remember again calculus 101. Before we've seen the rules of differentiation, we learn how we differentiate a function using limit. Remember? Not remember? Using limit. Limit as h goes to 0, we have f of x plus h minus f of x divided by h. This is derivative. Using limit, we can find the derivative of a function. At the beginning, people use this idea to get a derivative. And then they find the rules. And using the rules, you differentiate a function. So here the same. First, the limit, using limit. But I'm not asking you, I will not ask you to get the function, to find the derivative of the function using limit. Okay? Look at the example. If z, f of xy, is equal to this, x squared y plus y power 3 plus xy squared plus 5x. And you want to find derivative of z with respect to x. Okay, z with respect to x. That means here, y is, you consider it is a function, like a function, like a constant. Okay, y is constant here. So we have x squared y actually here, two things. So derivative x, 2x times y. Okay, and derivative of y, since derivative of y is a constant, that means 0. You don't write anything. Plus, this is what? This is constant. Derivative constant, 0. And here, this is constant. So this is something like that. Derivative is 5. Huh? So here, derivative is y squared. And here, derivative is 5. When you differentiate z with respect to y, this time, x is considered as a constant. So derivative x squared, 0, plus derivative of 3y squared, 6y, plus derivative of 2xy with respect to y, not y, 2x. Because this is a constant, so constant times y, for example, just derivative is 5. That's it. So this is the first derivative of two variable function. So in two variable function, if you want to take a first derivative, you have two derivatives with respect to x, with respect to y. Okay? Now here, the partial derivatives f with respect to x and f with respect to y give us the rate of change of f as each of the variables x and y changes with the other one held fixed. Okay, as I told you, they do not tell us how f changes when x and y change simultaneously. Okay, again, let us use the same example. You produce a cheese, white cheese and yellow cheese, for example. So you use different material for producing that type of cheese. Different material, that means different money you spend. Okay? And you want to maybe produce more white cheese than yellow cheese, maybe, and see what will your profit be. And you said, okay, if I change one more unit producing white cheese, what happened? If you change X this time, one more unit, but Y is held fixed, what is our profit? Okay, so you fix, you held one variable fixed, and you look at the other one, rate of change of the other one. It seems maybe at the beginning, it seems maybe a little bit complicated, but it's not complicated. I know it is very easy. Okay. Okay, we have a square root of here. Square root, maybe you confuse in the square root, maybe you confuse it. Let's say that, find it another example here. Easy example, and then I'm going to finish in 5 minutes. Okay, just I know you're a little bit boring, but we give that break now. Don't worry. Just try to be sure that you understood the partial fraction. Let me solve some examples. But first of all, I have to open new page. Yes. Now, okay. Suppose you have f of xy equal to, I don't know what, but let's say x power 5 minus x squared y power 3 plus 2y minus 3x minus 5, let's say. So find the derivative of f with respect to x. Del f over del x. Yeah, tell me now. 5x power 4 minus 2x y power 3. Okay, don't forget to put y power 3. Plus, this is 0, minus 3. That's it. Is it difficult? No, you see? So, what is del f over del y? 0, 3x squared y power 2 plus 2, then 0. 0, 0. That's it. So if you want to now take it second derivative. So you see, first derivative is another function here. So second derivative with respect to x again. So look at here now. 20x power 3 minus 2. That's it. Huh? Yes. Okay. Now fx, I mean here, first x, and then y. This time you first differentiate with respect to x, and now you differentiate with respect to y now. 0, 6x y squared, 0. Okay, then we have fy here. So fy and then y. Again y. 0. Here, 6, I mean minus 6 x squared y, 0, 0. And first y with respect to y, and then x. 12 x y. First y. Sorry. Y, where is y? Here. Sorry. Yes, here. First y, then x. 6x minus 6x y squared. Okay? So this is how you take a second derivative. So when you take a second derivative, you see you have 1, 2, 3, 4, 5, 6. To get all second derivatives, you should take 6 derivatives, okay? And do you realize something here? Just look at, check it. What you see here? What you see here? You see this term, negative 6xy squared, and this term equal, same. Okay? So this means that, I explained here. Note that the mixed partial derivative, yani x, y, for example, taken with respect to the same variables, but in different order, turn out to be equal. Always they are equal. Yani if you already know that derivative f xy is 6, fyx is also 6. You don't have to take it again and again. Okay? All right? You understand what I mean? All right? So in exam, 100%, like Calculus 101, remember, you have a derivatives question. So you will have a derivative questions, partial derivatives. Right? So this is partial derivatives. Any question? Any question? Any questions? No? You sure? Yes? Okay. So study well and don't forget, actually, I will give information about the quizzes, online quizzes on Uzebin. This Saturday, you will have a first online quiz. Okay? So see you on Friday. Yes. I don't know. I will check it. And if you don't have it, I will send to the photocopy center, right?
The sheet for this is it?
Yeah, I don't know whether I send it already or not. I will check it. And if not, I will send it and we can. All right. But anyway, you have online book.
Yeah.
So you can, it's the same as online book. So you can study online book. Okay, I know the students prefer the teacher's lecture notes, but it's already, everything is in from the online book. Okay. All right. Okay. Any question? Yes.